Okay, so hello. Today I'm going to talk about the action principle, and I'm just assuming that you know the intuition for the Lagrangian, like why do we form Lagrangian, what is Lagrangian, and you are at peace with the Euler Lagrange equation, like you understand what is Euler Lagrange equation. Even if you don't, I'm not going to do a hardcore proof from the Deleuze principle. Rather, what I'm going to do is I will just write the Euler Lagrange equation and show you that indeed it is the correct solution to the mechanics problem. Okay, so let us begin. And then we'll talk about action, and then we can again rederive these Euler Lagrange equations from the action principle. And then later we'll study the special relativity through the action principle, through the more general action principle, and then after that there is general relativity and so on. Okay, so let me just write what Lagrangian is. We will begin with the Lagrangian. So let's say we have a particle. Here is a particle, and let us say that it is under the influence of some force. So you are basically exerting some force on this particle, and hence this particle will travel some trajectory, arbitrary trajectory it will follow. Okay, let's say from T1 to T2 we are observing, so it has traveled this zigzag trajectory, okay, under the influence of some force. Okay, so the principle here is that we form Lagrangian using some scalar quantities called as kinetic energy T minus potential energy U. So this is a kinetic energy, and this is the potential energy. Okay, so this potential energy is the source of the force. So basically, I am here really saying that the force that we are considering here is a conservative force. Otherwise, you cannot write potential energy. However, there exists a more general formalism, or rather to include the dissipative forces like friction. You have more general formalism, but let us assume that we are considering only conservative forces, because the fundamental forces are conservative, so we are good to go here. Okay, so now let us just write for this. Since this is a single particle, we can write the kinetic energy T as half m r dot square. Okay, where r dot is basically the Newton's notation. It is just derivative of the position vector, and u can be a function of r and t as well. Okay, which is the potential energy, and it can be anything in general. So let us not worry about it, what it exactly is. Okay, so yeah, so now I'm going to write the Euler Lagrange equation. Euler Lagrange equation. So the Euler Lagrange equation is d by dt of del L over del R dot is equals to del L over del R. So when I'm writing in terms of this R vector, R dot vector here and R vector here, it is quite clear that it will be a vector equation. This is a vector equation which will incorporate everything. So we don't have to write in component form 1, 2, 3 component forms, which would be a little bit lengthy and time taking. Okay. So now let us write our Lagrangian first, which was T minus U. Here it would be half m r dot square minus U. Okay. So now let us perform derivative. So we have del L over del R dot. So del L over del R dot, because explicitly R dot only appears in kinetic energy. There is no R dot here in potential energy. I am assuming that there is no R dot in potential energy because it is a function of R comma T, I mean position vector and time. Simply a simple potential difference. Just to show you that it is correct equation. Euler Lagrange equation is correct. So it will be mr dot, okay, and del L over del R vector would be simply, it will be just minus del U over del R, because there is no R vector here. So the derivative with respect to R vector of this term, kinetic energy term, would be zero. Only the potential term survives. Now we can plug into this equation, or Lagrange equation, and we can write d by dt of m r dot is equal to minus del u over del r. But then d by dt of del r, d by dt of m r dot is, because m is constant anyway, so it can be simply be written as m double dot here and minus del u over del r. So this is what we get after solving the Euler Lagrange equation. But wait a minute, this looks familiar, right? The in terms of force picture, in force picture, which we are I think more familiar with, the force of conservative force is given by minus del u, which is gradient of the negative of the gradient of the potential energy, which you can also write in this notation as del u over del r. Okay, cool. So right hand side is the force, and what is the left hand side? So left hand side is just mass times double derivative of the position vector, which is just acceleration. So it is essentially giving you ma is equal to f, which is nothing but the Newton's second law. Okay, I think that is enough for first introduction. I mean, for the first video. Now, in the subsequent videos, what I will be doing is I will talk about the action principle, which I've promised here. I will talk about the action principle and then kind of derive this Euler Lagrange equation using the action principle. Because now you know that the Euler Lagrange equation, if we assume it freehand, it is working correctly. It is just giving you Newton's law, so it is correct. So now, if I derive it from the action principle, we are good to go. And then we can use these principles to then study the special relativity, which is the whole point of making this set of videos. Okay, bye.